Hello students, welcome to Sourav classes. The question 3 is, which is the correct order of degree of hydration among the following ions? So degree of hydration, we will say, is proportional directly to the, or inversely proportional to the size of ion. Okay, so we are saying what? That degree of hydration is inversely proportional to the size of ion. So what is the size of ion? What is the size of ion? Size of ion is obviously Be2 plus less than Mg2 plus less than Sr2 plus less than Ba2 plus. So smaller the size of ion, higher will be the hydration. So degree of hydration will be reverse order, isn't it? Be2 plus Mg2 plus Sr2 plus Ba2 plus. Next question is, consider the following statements regarding diagonal relationship of B and Si. Okay, so when they are saying diagonal relationship, what it means? Li, okay, Be, B, C, Si, okay, aluminium, magnesium, sodium. So when they're saying diagonal relationship, that means this type of a relationship. Okay, you can also see some diagonal relationship between beryllium and aluminium, also in lithium and magnesium. So this type of similarity of properties between boron and silicon, that is what they are hinting at over here. Okay. Now, electronegative values of both the elements are almost same, which is true. Both the elements have almost identical values of ionic potential. So what is your ionic potential? Obviously, ionic potential means what? Charge by the radius. Okay. This is your ionic potential. So this ionic potential and also electronegativity, which is En, also represented as chi. Okay, these two things, okay, for metals or elements which are diagonally related, they will be the same. So over here our answer is going to be option A. In the next question, it is given 5. Consider the following statements for lanthanum. It is a F block element. It is a F block element. It is an inner transition element. It is transition series element. It is a rare earth element. Okay, there is no doubt about it that it is a rare earth element. Besides that, we will say it is also a inner transition element. Okay, so over here, once we check the options, we will say it is going to be 2 and 4. That will be the correct elements. Okay. Now, why we are saying lanthanum to be as inner transition element? Because lanthanum is 57, okay, and it is obviously having the electronic configuration, we will say X E, okay, 4F, 5D1, 6s2. All right, that is why it is called the inner transition element. Next is argon is used in arc welding because of its high calorific value, ability to lower the melting point of the metal, low reactivity, flammability. It is not flammable gas, neither it has a high calorific value because it is not going to burn itself by itself. It cannot lower the melting point of a metal, but obviously because of lower reactivity, it is a inert gas, and so while welding of metal, it creates an inert atmosphere. Okay, which of the following represents the correct order of ionic radii among the following? Here one should remember that diionic, okay, or we say let's di negative anion. So this is on radius, okay. Size is more than mononegative anion. So this is radius of isoelectronic, okay, isoelectronic ions, which is more than that of monopositive. So positive charge reduces the size of the cation with respect to that of a neutral atom, and negative charge increases the size of a anion with respect to a neutral atom. Okay, so which will be more than that of di-positive cation. That being the case, we will say S2, which is isoelectronic with Cl minus, will be more than that of potassium, which is isoelectronic with Ca2 plus. So this is the order of radius. Okay. That being the case, we will say B is the correct answer. Dipole moment of HC triple bond Cl, CO and that of HCl are in the directions. Hydrogen is less electronegative than carbon, but chlorine is more. So obviously dipole moment is in the from left to right hand. In case of CO, also dipole moment is towards the oxygen because it is more electronegative than that of carbon. Similarly, in case of HCl, Cl is more electronegative than that of hydrogen, then dipole moment is from left to right hand side. So obviously we will say C is the correct answer over here. Consider the following pair of species of oxygen and their behavior. Okay, that is a question that has been asked. Now for this we need to draw the molecular orbital diagram. So suppose that is 1s, 1s. These two combine to give you sigma 1s, sigma star 1s. Suppose this is your 2s, 2s, and these are your oxygen atoms or atomic orbitals, that is AO. In the middle we have the MO of oxygen atom. Similarly, this is sigma 2s, this is sigma star 2s. Okay, This is sigma 2s. This is sigma star 2s, that is the anti-bonding. And let's now draw the MOs for the coming from the 2p orbitals of oxygen atom. So we have this followed by that one, then that one, and then we have, so that we will say is coming from the lower ones are the bonding MOs, and orbitals above, MO above the atomic orbitals are the anti-bonding MOs. So this is obviously coming from sigma 2p x, and this is say sigma star 2px. These ones we will say pi 2py, pi 2pz. These ones are pi 2p star y, pi star 2pz. Okay, that is your diagram or molecular orbital diagram for molecular orbital diagram for oxygen. Okay, that is what it is. And if we know that in oxygen there are obviously in the valence shell there are around 6 electrons. In total oxygen there are 8 electrons. Okay, atomic number of oxygen is 8. So now if we put the electrons, okay, obeying the Hund's rule of maximum multiplicity and from lower energy to higher energy, so all total the electron will be 16. So if you put the 16 electrons, then we find that there are 2 unpaired electrons in the anti-bonding MO of the oxygen. So oxygen by itself is paramagnetic. So when they are saying O2 minus, that means one oxygen has taken electron. So that means we will add one electron here. So that means one unpaired electron. So obviously we will say this is paramagnetic. O2 plus means what? We have taken out one electron from oxygen. So if you take out one electron from oxygen, now if you're taking out so one electron, that means one electron is left in the anti-bonding MO. So this also is paramagnetic. Isn't it? What about O2 2 minus? If you add now 2 electrons here and here, okay, if you're adding one electron here, another electron here, that means what? It becomes a diamagnetic system. So we will say this is diamagnetic. Alright, what about a simple O? Simple O. In the valence shell, so this is 2s and this is 2p. It is having two unpaired electrons, so this is also paramagnetic. What is the question now? Which of the pairs of oxygen species above represents correct magnetic behavior? Okay, so obviously this is diamagnetic, so it cannot be paramagnetic. Both are paramagnetic. First one is paramagnetic and the next one is diamagnetic. O2 minus is paramagnetic, O2 minus is diamagnetic, so this is wrong. O2 plus is paramagnetic, but O2 minus is diamagnetic, so wrong. O2 plus is paramagnetic, O2 minus is paramagnetic, as we can see out here. So this statement number 3 is going to be correct, and that should be the answer. Question here is, which of the following statement regarding the properties of the nitric oxide is true? Okay, nitric oxide gas is paramagnetic, but the liquid nitric oxide is diamagnetic. This statement is true. Okay, nitric oxide gas is diamagnetic, but the liquid nitric, obviously this is, once we have said it is paramagnetic, so it cannot be diamagnetic. All right, NO is basically, the N is sp2 hybridized and it has one unpaired electron, so it's odd electron system. Now in presence of liquid it becomes a dimer, which is N2O2, and that becomes diamagnetic, but this is paramagnetic. Nitric oxide is neutral. If it is neutral, obviously it cannot be an acid anhydride. Acid anhydride are those gases which, on adding water from acid, okay. Nitric oxide is neutral, they are saying, so this is correct. So obviously we will say 1 and 3 are correct statements over here, okay. In the next one, it is given which of the following have greatest ionic character. Obviously Cl2O, NCl3, NClO are nonmetals, and so its compounds are covalent in nature. Now among PbCl2 and BaCl2, Pb is post-transition element and Ba2 is earth alkaline element. Okay, Pb2 plus will be more polarizing than Ba2 plus due to lanthanoid contraction. So we can say more the polarizing power, more covalency. PbCl2 is more covalent than BaCl2, which means what? BaCl2 is more ionic. So obviously that is going to be our answer. Question number 12 is over here given. Consider the following statements of Madelung constant. Madelung constant typically increases with coordination number. That is true statement. Large contribution towards Madelung constant comes from the nearest neighbors. Okay, nearest neighbors obviously contributes towards the coordination number. And such neighbors are more numerous. That means it is larger when coordination number is large. Okay, so obviously statement number 1 is a correct statement, and statement number 2 is also a correct statement and a correct explanation of statement number 1. Okay, so we will say option 1 is going to be correct over here. In the next, it is being said which of the following represents the correct order of melting for the following. So for that, theory is smaller the size of metal ion, more is the polarizing power. Okay, and subsequently more and more is the covalency of the group 2 chlorides. Okay, that is one thing. So among the group 2 chlorides, we will say BeCl2 is more covalent. Okay, then MgCl2, which is more covalent than CaCl2. Okay, and among group 2 and group 1 chlorides are more ionic than group 2 chlorides. So here we are saying BeCl2 is less ionic than MgCl2 and MgCl2 is less ionic than CaCl2. Alright, that is what we are saying, and NaCl is more ionic than all the rest. So ionic character increases, melting point increases. Ionic character increases, melting point increases. Okay, so that being the case, we will say increasing order of melting point is given as follows, and that should be our answer. So over here we will say the correct answer over here is going to be option A. What kind of defect appears in the AgBr crystal? So AgBr crystal will be having flexibility or The radius ratio of AGBR, we can say radius ratio of AGBR is intermediate, and so because of this it can exist both as in Schottky or in Frenkel defect. Okay. Next, we have been given, consider the following statements. O2 molecule is diamagnetic. Okay, so this statement is wrong, as we have already shown. Okay, we have already shown here in the MO diagram, as you can see over here, that it is paramagnetic. All right, so O2 cannot be diamagnetic. So similarly, we will draw. Similarly, we will draw the MO diagram for the N2 molecule. So if we draw that, okay, these are the anti-bonding. 2s, sorry, 1s, 1s, 2s, 2s, 2p, 2p, n out here, n out here. 7 total electrons. So 1, 2, 3, 2, 3. If you fill up the electrons, it is all total 8. Right, we have 9, 10, 11, 12, 13, 14. So it is obviously diamagnetic. Okay, N2 is, we will say, diamagnetic. So obviously statement is wrong. Statement is wrong. So 1 and 2 are wrong. 1 and 2 are wrong. That means obviously A option and B option are also wrong. D option is also wrong. So only 3 can be right. Okay. Only 3 can be right. So that way we will say our answer over here is going to be CO has more bond order than neutral CO. Okay. Why so? CO plus has more bond order than neutral CO because the HOMO of CO is slightly anti-bonding in nature, and so reduces the bond order of CO. However, on removal of electron from HOMO, that is formation of CO plus, the bond order increases. Okay. So that is the explanation why CO plus has more bond order than the neutral CO. Okay. So this is the explanation. Next, NH3, NH4 plus, NH2 minus. Okay, the correct bond angles among the following. We know that lone pair repulsion is more than lone pair bond pair repulsion, more than bond pair repulsion. If we consider that way, NH4 plus is sp3 hybridized and having a regular tetrahedral structure with no lone pairs. So there is only bond pair repulsion over here. Say suppose this angle is over here x. In the NH3, again nitrogen is sp3 hybridized, but there is a lone pair bond pair repulsion out here. So angle y will obviously be less than that of x. In NH2 minus, just like water, it has two lone pairs. So the angle z, there is lone pair repulsion, lone pair bond pair repulsion. So angle z is going to be less than that of y. So x less than, more than y, which is more than, and y is more than z. So that should be our answer, and that way we will say option B is correct. Again, question on oxygen. It says statement potassium superoxide is paramagnetic. Why? K plus O2 minus. Okay, and we have already shown that O2 minus, in this discussion only, we have shown O2 minus is paramagnetic. Okay, the superoxide O2 minus is paramagnetic because it has one unpaired electron in the pi star 2p molecular orbital, which is true, and that can be shown by the MO diagram. So let's do the MO diagram again. This is say 1s, 2s, 2p. So this is 2s, sorry, this is 1s, 1s, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, this is sigma 2pz, sorry, x, and that is pi 2p x, sorry, z, pi 2py, pi star 2p y, pi star 2p z, and this is sigma star 2p x. So the electrons, let's fill this up. 8 electrons for oxygen each. So this is oxygen AO, this is MO of O2, and that too is oxygen AO. If you fill up the electrons, just follow how I'm filling it up. So this is molecular orbital diagram for O2. You add one electron, it becomes O2 minus. So this is O2 minus, and we can see in the O2 minus, pi star is having one unpaired electron. Okay, so that statement is true. So we'll say both the statement 1 and Two are true and 2 is the correct explanation of that of 1. So this is the going to be the right answer. Next, we will go for question number 19. In question number 19, it has been given what are the spin only magnetic moments for Ni ion in square planar and octahedral complexes or octahedral geometry. Nickel 2, nickel 2. In one it is square planar, in the other it is octahedral. So splitting in such fields will be something like that. D8 system for both. So obviously n value over here is 0. Mu is nothing but root over n into n plus 2 bm, and that is going to be 0 bm. For this one, however, it is going to be T2G set and EG set. So there are two unpaired electrons, n equal to 2. So mu as value n plus 2, and that is 2.83. Bohr magneton. Answer will be this one. In which of the following complexes is tetrahedral and diamagnetic? So out here it says tetrahedral and diamagnetic. Ni NH3 4 2 plus, or say NiCl4 2 minus. These are tetrahedral, but D8 system. ET2. These are always high spin, so they cannot be diamagnetic because there are two unpaired electrons out here. Okay, as we can see, there are two unpaired electrons out here, so cannot be diamagnetic. Similar explanation for NiCl4. For NiCO4, okay, it is 0 system. All right, that means it is D10. So obviously out here we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So obviously this is n equal to 0, and so diamagnetic. All right, and this is also tetrahedral. What about NiCN4? This again, it is a D8 system. Okay, this is a D8 system, but NiCN4 2 minus D8 system. Now this is square planar. Okay, so obviously our answer here is going to be option C, which is NiCO4. Which of the following will not precipitate AgCl in the next question? 21. AgCl, while reacting with the excess of AgNO3 solution at room temperature, oxidation state of cobalt 2 in all the complexes, it is 3. Okay. CN for CO is equal to 6. Okay, keep that in mind. We can say that for this one, we will say it is CO NH3 whole 6 CCl3. For the B, we will say it is CO NH3 whole 5 Cl2. So we can see already the ionization sphere in our above complexes are having Cl. In the A it is 3 Cls and in the B it is 2 Cls. Okay. So this will give test with the AgNO3 and will give a precipitate of AgCl. Which one will not give? One that is not having any Cl outside that in the ionization sphere. So for the next one also it is Cl2 NH3 whole 4. This is also having Cl in the ionization sphere, so this also will give test. What about D? It is NH3 whole thrice. It is having no Cl in the ionization sphere, and so we will say our answer over here is going to be this will not give any precipitate with AgCl with excess of AgNO3 solution at room temperature. Okay. Which of the following complexes cannot ionize? It cannot ionize, that means there are no ions in the ionization sphere. Okay. Complex A is having 4 Cl in the ionization sphere. So obviously it will give ions in solution. Okay. It will give the ions in solution. Even in complex B we are having potassium, 2 potassium in the ionization sphere. So obviously this also will give ions in solution. In K4 FeCN6 also we have 4 potassium in the ionization sphere, so it will also give ions in solution. And what will be those ions? If we just say it is going to be Pt NH3 whole 6 4 minus 4 Cl minus all this aqueous. Okay. What about the next case? 2K plus PTF6 2 minus all aqueous. Okay. In case of this K4, it will be 4K plus aqueous FeCN6 4 minus. Okay. But for D, there are no ions in the ionization sphere, so we will get no ions. Maximum density of the polydentate ligand tetraethylene pentamine is equal to. Structure of tetraethylene pentamine is what? So this is tetraethylene pentamine, and that way if you want to predict the structure, the density of the this particular ligand, so it will be obviously dependent on the maximum number of lone pairs available from every donor site. So this is 1, 2, 3, 4, 5. So this is going to be 5 the answer. Correct IUPAC name of K2ZnOH whole 4 is, so simply name of the cation first, it should be potassium. Okay. Zinc is in the negative part of the complex, so it should be zincate. Oxidation state is 2, and the ligand in the coordination sphere is OH, which will be called as hydroxido. There are 4, so it should be tetrahydroxido, and should be zincate, not zinc, and ended may it should be the oxidation state 2. So obviously our answer here is going to be B. Okay, not B, rather it should be this one, C. Next we have, which of the following octahedral complexes does not show geometrical isomerism? So geometrical isomerism can be shown by Ma2B4. How? Let's have a look. B, 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 B. You have the A in the transform. Okay. Then we can have this in the cis form. So this is trans, this is cis. Okay, so this will show GI. What about MA3B3? MA3B3 will show FAC-MER, that is facial meridional isomerism. Okay, this is your FAC, and in case of MER, keep the two A's trans to each other to produce the MER, or the B trans to each other. Okay, so this is your meridional. So this is also showing GI. What about C? C also will be showing GI. How? We have A, A. So this is your cis, and that should be your trans. Okay. However, for D, since there is only one B, so it cannot show any GI. So obviously our answer here is going to be D. Okay, now for the chromium, the oxalate ligand is like this. So we will write it as something like that. Okay. For En, it is something like that. This is our En. This is our oxalate, or C2O4 2 minus. Okay. And we will write this as, for our convenience, like this. Okay, keep that in mind. So it says, which of the following will not show optical isomerism? So if you are having chromium, okay, the idea is to place all the O in the octahedral positions. So we have like that, and like that. Charge outside the complex will be 3. Its mirror image, so this is showing optical isomerism, we can say. Similarly, for cis PtCl2 En2 whole twice. This is the one, and its mirror image will be so. That is how it is. In case of COEDTA, okay, this is how it is. Okay, and this will also be having one mirror image. Similarly, and okay, let me now erase this part because we do not require this one. So this will be CO. Okay, so all these are having A, B, C are having mirror images, but D will not have mirror image. It will only be having showing GI. Okay. Next question is 27, in which how many isomers are possible for COEN2 whole twice, En2 whole twice, and Cl2? Obviously, the answer here is going to be C. Let's have a look. What are these? So we have for En, I have already told you that we will be using this type of notation for the convenience. So this is your trans. Okay. And for the cis isomer, we can draw two mirror images, which is obviously going to be like this, and the other. So these are the two mirror images, whereas one is related to two or three as GI. Okay, obviously the total is going to be over here. As we can see, it is 3. I hope that explains the questions that were asked in this particular exam in relation to inorganic chemistry. And keep visiting Sourav classes. This is Dr. Sarkar over here. Thanks for listening. Have a great day.